Now, let's look at this world of Bayesian credibility. So, we'll try to get into the study of the credibility theory using the Bayesian approach. So, whenever we are bringing in the Bayesian approach, we are always talking about an unknown parameter. So the prior distribution of the parameter comes into picture because we talk about any kind of a data that follows a distribution. We are making an understanding there that the parameter's value is unknown, and it need not be fixed also. It follows some kind of a distribution. So initially we assume some distribution to that parameter, and that is what we are calling as the prior distribution. And after that we collect the data. From that data of that underlying, we try to come out with a likelihood estimate for the parameter, and based on the likelihood and the prior, we multiply the prior with the likelihood estimate to finally come out with the posterior. We try to arrive at the distribution of the posterior, and once we have computed this posterior, we'll use an appropriate loss function on the posterior distribution. It could be a quadratic loss function, or an absolute loss function, or all or nothing kind of a loss function. Any of these loss functions we'll use and come out with a Bayesian estimate. This is how we typically estimate the parameter whenever we bring in the Bayesian theory into consideration. Now, here also, the same credibility theory we will try to explain using the same concept of Bayesian approach. Here we will look at two major kinds of models. One typically for modeling the frequencies, where we'll talk about Poisson gamma model, and two, we will look at modeling the claim amounts, wherein generally normal model is used. Now, if I understand this in a very simpler sense, when I look at this frequency, now here I am making an assumption that the expected number of claims, right now I'm going with expected number of claims in a particular year. In the coming year, I want to estimate, right? I want to estimate the frequency of the claims for the next period. So what we typically start with is we are breaking this problem into two parts. The number of claims, the frequency of claims each year, it follows Poisson distribution. So we are making that the frequency of claims it follows a Poisson distribution with a parameter lambda. The parameter lambda is not known, but it is having some kind of a distribution. So there is a prior distribution for this lambda. So this is what I say, the prior distribution of lambda is a gamma distribution with parameters alpha and beta. So for this lambda, I know that the mean is alpha by beta and the variance is alpha by beta square. Now, so this is the prior distribution, right? This is the prior distribution. So I can very well get the frequency, I can very well get the probability density function for lambda, right? So I'll get my f of lambda, which is the probability density function. What is the probability density function that is associated with a gamma distribution? We can very well get it from the typical tables. We will get it as beta to the power alpha divided by gamma of alpha times beta to the power, lambda. Lambda to the power alpha minus 1 e to the power of minus beta lambda. This is what it is. So this is what is the prior distribution of the gamma. And now I am collecting the data. Probably I have collected, let's say, n for last n years, I have collected the claims. Now these claims are going to give me some kind of information regarding the likelihood. Right, I have collected the claims, original claims, and they have given me the likelihood. Now, if I have collected the claims like x1, x2, x3, so on, xn, right, what is that mean number of claims here? The mean of this particular distribution will give me sigma xi by n. This would be the mean number of claims. Whereas going with lambda, I am getting that the mean number is alpha by beta. So from my actual distribution, if I'm looking at my past data, I'm trying to find out the mean, I'm getting it as sigma xi by n. But if I'm assuming that this lambda is following a gamma distribution with alpha and beta, the mean is coming out to alpha by beta. So here the two parts are the frequency of the claims is following a Poisson distribution with a parameter lambda. Lambda is following a gamma distribution with parameters alpha comma beta. Right? So this is what is typically working out. Now, now I'll go with a posterior distribution. I have to compute the posterior distribution. All right. Now, if I look at the prior, which is a gamma distribution, I can very well say that the prior is beta to the power of alpha. What is the prior in case of we have already seen for the gamma distribution. So I'll write it as beta to the power of alpha by gamma of alpha, lambda to the power of alpha minus 1 e to the power of minus beta lambda. This is the prior. Now what is the likelihood? I am taking this from a Poisson distribution. Lambda per x e to the power of minus lambda by x factorial. This is what is for each one. Now, if I have to take it for each of the observations, it is okay. If I take it as x1 factorial becomes the probability function for the second e power minus lambda into x lambda to the power of x2 divided by x2 factorial and so on. So overall, the likelihood function is becoming the multiplication of all this, which is coming out to lambda to the power of x1 plus x2 means sigma xi e to the power of minus n lambda, right? And probably the denominator x1 factorial into x2 factorial, so on. It's becoming a kind of a constant. Because here my intention is primarily looking at the estimation of the parameter, which is lambda. So x1s I really need not take into consideration. So if I'm multiplying this with this, it becomes lambda per sigma xi e to the power of minus n lambda. Now, if I really look at this posterior distribution, it is more or less proportional to, I take only the lambda related stuff. So it is proportional to lambda to the power of alpha minus 1 plus sigma xi and e to the power of minus of beta plus n times lambda. Now if I see, this is more and more similar to that of a gamma distribution with the parameter alpha plus sigma xi and beta plus n. This is what is the posterior distribution. Now I can find out the mean of this posterior distribution, right? The mean of this posterior distribution, because it is gamma distribution, the mean of it comes out to alpha by beta, which is alpha plus sigma xi divided by beta plus n. So this is the mean of the posterior distribution. Now I want to break this into the credibility theory kind of a mechanism, wherein I want to give some z weightage to x bar and some mu, some 1 minus z weightage to mu, which is from the historical. Now what is my x bar here? Whatever is the mean that I am getting when I am using purely my own risk data. X1, X2, X3, so on. X1 is my risk data. So X bar is nothing but sigma Xi by N. So whatever is the weightage that I get through sigma Xi by N. And here mu for me is based on the prior distribution. So the mean is alpha by beta. So I want to split it into that kind of a mechanism, where I'll give some weightage to sigma xi by n and some other kind of a weightage to alpha by beta. So this is what I'll try to break. Okay, alpha by beta plus n plus sigma xi divided by beta plus n. Right? Now what I'll do here, both the numerator and the denominator I'll divide by beta. Right? If I am dividing both of them by beta, it is nothing but alpha by beta divided by beta plus n. Sorry, beta plus n by beta. This is fine. And this part also I'll make it sigma xi by n divided by beta plus n by n. Now if you look at this, write it the other way. So this is nothing but mu. So mu times, I'll call it as beta by beta plus n, whereas this is sigma xi by n is nothing but x bar. X bar times n by beta plus n. Now this has to be my z. So I can very well say z is n by n plus beta. So 1 minus z will become 1 minus of n by n plus beta, which is nothing but n plus beta minus n by n plus beta, giving me beta by n plus beta. So which is nothing but this becomes 1 minus z. So it is actually getting written in the form of a credibility estimate, z times x bar plus 1 minus z times mu, where z is coming out as n by n plus beta, where beta is an estimate from the prior distribution, n is the number of years of data that I am typically collecting from my historical, right? So the overall estimate of the posterior distribution is very well getting expressed in the form of a credibility estimate. Some weightage going to the mean number based on the prior belief, and some weightage going to the mean that is computed from the prior gamma distribution. And Z in this case, the credibility factor is coming out to n divided by n plus beta. So now if you see, okay, Z is n divided by n plus beta. So if I did not have any historical data, I did not collect any kind of a data for my risk, which means n equal to 0. So the Z is directly 0. Means I'm relying completely on the credibility on the collateral data itself to come out with the estimate of my claims for the next year. So the best estimate in that case is just the mean of my historical prior distribution, which is alpha by beta. But on the other side, if I had purely N only my historical data, only the risk-based data, but I don't have any other benchmark or collateral kind of a data, then Z is working out to be 1. Means the full weightage that I am giving in terms of estimating my claim frequency for the next period is purely based on my historical data, which is coming out as sigma xi by n, which is nothing but the maximum likelihood estimate that I am getting for my historical data. So if you look at this, the value of Z is completely dependent on the amount of data, how many years of data that is available for my own risk, and also with respect to the collateral. How much of data, what is the kind of, see, beta is actually a measure of a variance as a part of the parameter. But again, that value of that particular parameter is helping me understand what is the kind of credibility that I have to give, which means as I am increasing n, as n is increasing and increasing, we see that the credibility factor that we are giving to our own data is actually increasing drastically. And as we know, for the prior distribution, right, the mean is alpha by beta, the variance is alpha by beta squared. So beta squared is going to reflect, beta squared or beta is going to reflect the variance heavily, right? If beta is higher and higher, what we see is the variance of the estimate is going much lesser. So as the beta is increasing, the reliability on the collateral is going to be much higher because the variance of the estimate is actually coming down. But for a lesser beta, probably the credibility factor is going to be much higher. So whatever is the Z that is coming out, even it is this kind of a mechanism is clearly bringing out the relative reliability that is associated with both these estimates. So here we are looking at the lambda can be purely based on the historical. The lambda could be purely based on some collateral data from the external, or it could be some kind of a weightage that could be distributed between these two kind of models also. Now let's take one simple example to understand this entire process, right? Let me put these numbers as a part of the spreadsheet, right? Okay, I am looking at the number of claims using this Poisson gamma model, right? And here we are taking, let's say lambda is 150. So which means the Poisson model for distributing the claims, for the distribution of the claims, we are saying that it follows a Poisson distribution with 150. But of course, at the same time, we are saying that the lambda on an average is following a gamma distribution with parameters 100, 1, which means the mean of this gamma distribution has to be 100 by 1, which is 100. And the variance of this prior distribution is 100 by 1 squared, which is 100, which means the standard deviation of this should be equal to 10, right? Now, let's take the actual number of claims, right? This is the prior. Now, let's go with the actual number of claims. Okay, I'll take, let's say I've got the data for the last 10 years. right? I've got the data for the last 10 years. I'm looking at the actual number of claims. So let's say I have 144, 144, 174, 148, 151, 156, 168, 147, 140, 161. Let's say these are the actual number of claims that we have got. Now, based on this, I really want to see how the credibility factor is changing. Now, we know that the beta is 1. So, I can very well find out the credibility factor based on our earlier formula. The credibility factor actually comes out as n by n plus beta. So, n divided by n plus beta is always 1. Right, n divided by n plus beta. N is this one plus beta. So the credibility factors are coming like this. Now what I can very well do, if I am trying to plot between this and this. Now let me look at a simple graph which plots the credibility factor. The credibility factor is typically increasing. Means in the first year, I'm giving only a 50% weightage to my original observation, to my risk-based observation. Whereas the remaining 50% I'm giving to the collateral, which is the prior distribution here. The collateral data here is the prior distribution. Now, based on this, so when I'm saying credibility factor, this is the amount that is going out to these data points. So we can very well find out the X bar. The X bar which we are computing from our data. So I can always take it as average from whatever is the data that is available. So here I'll take the average for the first year. I'll take average of only 1 year's data. Only 1 year's information is available. Whereas when I go towards the second, I have more information. So I'll typically take the average of 144 and 144. Whereas when I come here, I'll take the average of these three numbers to give the estimate for the next period. So this is what will become my X bar in each of these periods. And my mu in all these periods is going with the gamma distribution alpha by beta. So the mu in all these cases is 100 only. So because this is my credibility factor, I can very well give my estimated value. Estimated value is nothing but z times the X bar plus 1 minus z times the mu. Now this is giving me the estimated for the next period. Now this is giving me these are the estimated numbers. These are the actuals. These are the estimated in each of these periods. No, these are my actuals. These are the estimated. Now I can typically do a plot of these two. Right, let me look at how this plot is coming out. I'll do a simple line chart between the actual and the estimated. What I could clearly see is the estimated has been growing because more weightage is coming to the our own data. And probably in this example, what you clearly see is mu is a very underestimated kind of a number. In reality, our claims were nowhere closer to 100, which means the reliability on this should become lower and lower if our estimate has to improve. And this is what has happened in this example exactly. So the credibility factor, first of all, is increasing with time. The more and more of the historical data that I am collecting, the more is the credibility that is getting associated with the risk specific kind of a data. and higher is the credibility factor that is coming out, because n divided by beta plus n is always a kind of an increasing function. And now in the same example, right, instead of looking at gamma 100 comma 1, I want to look at gamma 500 comma 5 kind of a distribution. Why? In this case also the mean probably is 500 by 5 alpha by beta, which is still 100. So both this as well as this will have the same mean, but the variance wise, you see it is 500 by 5 squared, right? It's around 20, and standard deviation is somewhere around 4.5, the square root of 20, which is much lesser than this. So how does our estimate come out in that case? That is what I wanted to see. This will not, even this will change now. The credibility factor is going to change. Let's see what is happening to the new credibility factor here. It's simply becoming n by n plus beta. Now beta is 5. N by n plus beta. Now what we are seeing is the credibility factor that is going to our own data is becoming much lesser compared to the earlier case, because in the earlier case the volatility of the prior estimate was much higher compared to the current scenario, and because of that reason the less weightage was coming to that collateral or the prior distribution. The reliability on the prior distribution has actually come down, because there was a more and more volatility that was there in the prior distribution. Whereas now that the volatility in the prior has actually gone down, it looks like more weightage is going towards the prior distribution. So that's one more important point that is coming out here, right? And if I am doing an estimate now using that mechanism, let's say I want to do an estimate where it is coming out like z times whatever is my historical average. Historical average is this number, right? We have already computed. Z times the historical average plus 1 minus z times the value that we are giving to the collateral. The value that we are giving to the collateral, this one. So this is resulting in an estimate only 135, and probably if I am taking this data also into this chart, right? If I am taking this data also into this chart, all I could see is I'll call this as new. Now this is what is coming more to the newer estimate. The new is much below in almost all the cases. This looks slightly more smoother compared to our earlier case, right? And it's always lesser than the actuals, because the weight that it is receiving, the more and more weightage is going to the prior in this case, because prior is not having too much of volatility in itself, right? The estimated number of claims based on the collateral, though it is same for both of them, the standard deviation in case of the prior, which is coming from gamma 500 comma 5, is much lesser compared to that of 100 comma 1. So because of the standard deviation being much lesser, I'm placing more confidence. I'm trusting this prior very heavily. I'm placing more confidence on the prior, on that initial estimate of the number of claims using this prior compared to the earlier prior. So the smaller is the standard deviation of the prior, I'm giving more and more credibility, more and more relevance to that particular observation. That is one more important thing that we may have to bring out as a part of our understanding of the credibility factor that is being given, right? Now, on the other side, I will consider one more example, which is a normal kind of a model. Again, I estimate that the amount of claim will follow a normal distribution with a mean theta and variance sigma 1 square. At the same time, I say theta will follow another normal distribution with a mean mu variance sigma 2 square. Right? So this is the prior associated with the normal distribution, and this is for the data. So I'll take the data of the various claim amounts which are following this kind of a distribution. Now based on this, I would like to work out the posterior. Okay, what is my prior here? Right, theta is following this kind of a distribution. So the probability density function is 1 by root 2 pi sigma 2 squared, sigma 2, sigma 1, mu, all of them are known, only theta is a random variable here. 1 by square root of 2 pi sigma 2 squared e to the power of minus half theta minus mu by sigma 2 whole square. This is of the prior, and when I'm looking at the likelihood of the original data, this is coming out as 1 by square root of 2 pi sigma 1 squared e to the power of minus half x I minus theta by sigma 1 whole square. This is what is coming out. So for everyone, if I take, probably I can omit this because there is no theta 1 here. So overall, it is, if I am going with the likelihood, it is coming out as e to the power of minus half x1 minus theta by sigma 1 whole squared plus, or probably minus half x2 minus theta by sigma whole squared. So this is working out to xi minus theta whole square. So probably if you are looking at taking this as the likelihood, right, I can take the half out, which is working out to xi minus theta by sigma. So summation of, so e to the power of minus half xi minus theta by sigma 1 whole square. And this part, when I am bringing in the prior, it is also becoming e to the power of minus half theta minus mu by sigma 2 whole square. So overall, it's again some kind of a normal distribution itself. So the posterior distribution here is coming out to be again a normal distribution, right? The posterior distribution of theta. Now I can very well try combining all these things. The mean will come out as mu sigma 1 squared, right? You can add these things up, right? So probably when you are adding these things up, this is coming out as mu sigma 1 squared plus n sigma 2 squared x bar. See, otherwise probably let's look at it. E to the power of minus half theta minus mu by sigma 2 whole squared plus sigma xi minus theta by sigma I whole squared. Now if you try adding up all this, right, I'll take e to the power of minus half Okay, sigma I, let me do with this. So this works out as theta minus of, I can very well look with mu sigma 1 squared, right, minus of mu sigma 1 squared plus n sigma 2 squared x bar. So this sigma xi squared, I am writing it as n times x bar divided by sigma 1 squared plus n sigma 2 squared, right, because sigma 1 squared, if I am multiplying n times, it is becoming n sigma 1 squared. So this divided by sigma 1 squared, sigma 2 squared divided by sigma 1 squared plus n sigma 2 squared. So this is becoming a normal distribution with mean mu sigma 1 squared plus n sigma 2 squared x bar divided by sigma 1 squared plus n sigma 2 squared, and a variance of sigma 1 squared sigma 2 squared divided by sigma 1 squared plus n sigma 2 squared. Now I could very well break down this mean. Now expected value of the posterior distribution is coming out as mu sigma 1 squared plus n sigma 2 squared x bar divided by sigma 1 squared plus n sigma 2 squared. Now the same logic, probably I'll break it out, mu sigma 1 squared by sigma 1 squared plus n sigma 2 squared plus n sigma 2 squared x bar divided by sigma 1 squared plus n sigma 2 squared. Now this is the x bar part. So I'll typically, if I say z equal to n sigma 2 squared by sigma 1 squared plus n sigma 2 squared, it very well comes out that 1 minus z should come out as sigma 1 squared divided by sigma 1 squared plus n sigma 2 squared, which is nothing but this is 1 minus z. So this is coming out as 1 minus z times mu plus z times x bar, which again exactly is coming in the form of a credibility estimate. Now in that case, it is coming out like z is working out to n sigma 2 squared divided by sigma 1 squared plus n sigma 2 squared, or probably I'll bring this to the bottom. So this works out as n divided by sigma 1 squared by sigma 2 squared plus 1. So this is what is becoming my credibility factor in case of this normal kind of a distribution. So the weightage, again something to x bar, which is the solely based on the risk itself, and mu that is available if no data from the risk is available to us. And this value can lie between 0 and 1. It is very positively related with n, which is the number of periods of historical data that I am able to collect, as well as sigma 2. Sigma 2 squared is a measure of the variability that is associated with the prior. So the lesser is the variability that is associated with the prior, this ratio will be higher. This ratio is higher means the denominator is higher, so the credibility factor is going down. Even in our earlier example, we were able to make a similar kind of a conclusion, right? So majorly, if we see whether we are looking at a Poisson gamma kind of a model or a normal kind of a model, the approach that we have used, which is first get the prior, then get the likelihood, go with the posterior, from that particular posterior go with a loss function, and whatever is the estimate that is going to minimize the loss function. We have already discussed, if we were using the quadratic loss function, the mean of the posterior is a Bayesian estimate for the random variable, and that's the reason once the posterior, we knew that it was a Poisson, it was a gamma distribution in case of the first and a normal distribution in case of the second. The mean of that, we have directly taken it as the Bayesian estimate. So everything remained more or less the same, only the distributions of the prior as well as the likelihood that changed in both the cases, right? And So I mean, it was more and more a simplistic kind of an approach, right? We have taken that the collateral data is can be very comfortably be estimated using a particular distribution, right? In this case, the collateral, we have directly said it follows a gamma distribution with alpha and beta. In this case, we said that the collateral is going to follow a normal distribution with mu and sigma 2 squared. So we have really made a very clean assumption in terms of the distribution that is followed by the collateral. And based on that, it looked quite simpler in terms of working out. But first of all, is this Bayesian estimate really acceptable? If it is acceptable, what should be the real values of this beta and sigma 2 square? So what is that needs to be aligned or assigned to as the parameters of that particular prior distribution? That we did not talk about. That's a real challenge. And in some cases, probably this kind of an this kind of posterior distribution may not result in. So the estimate, whatever we are getting, the posterior estimate, the Bayesian estimate that we got through the posterior distribution, only for some combinations we may get that we can directly rearrange in the form of a credibility estimate, whereas in many of the cases it may not be possible to rearrange in the form of a credibility estimate. So it may not work in all the situations like this. So we have to be really understanding the limitations of this particular process so that we can use it more and more effectively as a part of our mechanism for predicting either the claim frequencies or uh, uh, the claim amounts with much more reliability giving to the data. All right.